I promise this unit is going to be shorter than the last. So for this section, we're going to be doing a lot of our computing using Desmos. So definitely have that at the ready. So for multiplying and dividing rational numbers, we are just going to give a brief overview of what that notation looks like when they're asking us to either multiply or divide these rational numbers. And then we'll define multiplicative inverse and then touch a little bit on the variety of problems that we will see and apply. So let's look at the different ways we can be asked to multiply two numbers, which is the same as taking the product. Multiply is the same. We're going to take the product of two numbers. A nice one that we're used to seeing is 3 with the little x and 2. 3 times 2. How else can we express that? We may see, oh no, that is the product. That's not what I meant. We may see 3 with a little dot, 2. And you'll notice it's not a decimal. It's 3 and the dot is a little higher up. And that means these are equivalent statements. That's saying take the product of 3 and 2. And then you will also see the use of parentheses. All of those are asking us to evaluate the product of 3 and 2, and all of those would result in 6. All right, so then the next one is division. And division, we've just got a couple of different ways. So if, for example, I'm taking 18 and I'm asked to divide that by 6. I can see the division symbol, that division notation, and we have also worked with 18, and then we've got the fraction. Again, when we're talking about equivalent statements, these two are equivalent statements. They are both asking me to divide 18 by 6, and they both would have a quotient, meaning the answer of that division, the quotient would be 3. Lovely. So then there is this definition of multiplicative inverse. What is a multiplicative inverse? It is pretty much a reciprocal for a number. So if I had some real number a, its multiplicative, I'm just going to call it mi, its multiplicative inverse would be 1 over a, right? It's the reciprocal. You flip them. You flip them. So the multiplicative inverse of, let's say, 2/7. Its multiplicative inverse would be 7 over 2. They are multiplicative inverses of each other. Let's throw one out here. What if I had 15? What if I'm looking for the multiplicative inverse of 15? First thing I would do is I'd make 15 into a fraction. Let's throw a 1 under it. So 15 is the same as 15 over 1. So what would the flip of that be? Well, it would be 1/15. And the last one might be one that looks like a mixed fraction. 2 and 2/5. What's the multiplicative inverse of that? So then we go back and we remember, I can change this into an improper fraction. I can take 5, multiply it to 2, that gets me 10, and then I add that product by this number. So 5 times 2 is 10, plus that 2 is 12. So this is also 12, and then keep the denominator. So 2 and 2/5 is 12/5, and its multiplicative inverse is 5/12. Let's take a look at this problem so that you can do a practice one that's similar to it. Now you'll remember, I'm going to change both of these to improper fractions. I'm going to change both of these to improper fractions. And that is 3 times 3, which is 9, plus 1 is 10. 10, keep the denominator. 10/3 is that first number, times. Now let's do the same thing. 10 times 2 is 20, plus 3 is 23 over 10. Now, Do we remember our rule when we are multiplying fractions? That rule is top times top, bottom times bottom, top times top, bottom times bottom. So let's go for it. So then this results in 10 times 23. That's 230 over 3 times 10, which is 30. And you all might remember that if you have a 0 on the top and the bottom, boop, boop, they cancel out, and we're left with 23 over 3. And just so we're clear with that last example, you can see in Desmos, I typed in for the first bar, the first cell, the way that we did it. We changed those mixed fractions to improper fractions, 10/3 times 23/10, and that left us with that decimal. And if we hit the fraction symbol on the left, it converts that to 23/3. And you'll notice on the bottom, that's the same question, except I kept it in that notation. I kept it as 3, don't forget, and mathematically speaking means plus. 3 1/3 times 2 3/10, and I can write it just like so, and that also gives me the same result. Now here we've got some rules that we can follow when we're multiplying and dividing, not just integers, but rational numbers, real numbers that have different signs. So let's look at just a couple of these as we go. And the first rule that follows, and this is for multiplication and division, is that if I take the product, if I multiply or divide two positive numbers, my result is also a positive number. And here to the right, you see two different examples of how that looks. Now, the one that we want to also keep in mind is a negative times a negative is a positive. So, example 1 for multiplication, -2 times -5 is positive 10. And then one for the quotient for division, -48 divided by -6 is 8. And I sandwich these two together because they are essentially saying the same thing. If I take a negative number and multiply it to a positive number, that result is a negative number. And so an example for each, multiplication and division, are right there. One thing that I think is helpful to keep in mind is oftentimes, so let's say I don't actually care what the number is, but I'm looking at the signs, right? I got something like this. It's -1/4 times -4 times 9. Is what I like to do for these problems is first identify what my product is going to be. What's the result going to be sign-wise? So here I know a negative times a negative is a positive. Those two negatives just canceled each other out. Then I'm left with a positive, I'm left with the positive number times a negative number times a positive number. So a positive times a positive is a positive. And then I've got that result times a negative. So I know this is going to result in a negative number. What is useful to do is sometimes just to count how many negatives are there in this expression. 1, 2, 3. If there are an odd number of negative numbers, that's going to be a negative value. If there are an even number of negative numbers, that's going to result in a positive value.
What are you saying?
I say he'll flip you.
He'll what?
Flip you. Flip you for real.
Yeah, I'm shaking.
Now, the last thing is, let's talk a little bit about dividing when we are working with fractions. And I put here, and you want to make a note of this, that dividing by a number is the same as multiplying by that number's reciprocal. What does that mean? So let's look at this first example. We've got 7/5 divided by 3/2. Dividing by 3/2 should be the same as multiplying by its reciprocal. The reciprocal of 3 over 2 is 2 over 3. So there's something that I like to think of. I do keep, change, flip. Keep, change, flip. That means I keep the first number. So I keep 7 over 5. I change the division to its nemesis or its inverse. Multiplication. Keep, change, and what do I do with the 3 over 2? I flip it. Keep, change, flip. And then I multiply through. Top times top, bottom times bottom. So 7 times 2, which is 14, over 5 times 3, which is 15. On a roll, on a roll. So let's do the same here. You see 2/9 divided by 8. Ooh, and for our purposes, let's call that 8 over 1. So we're keeping, we're changing, we're flipping. Keep 2/9. Change division to multiplication, and I flip 8 over 1 so that it's 1 over 8. And then I multiply through top times top, which is 2 times 1, over, and then 9 times 8, which is 72. And if I wanted, I can use Desmos, or I can simplify that to 1 over. Here's how it looks if we were doing this on our own. 1/2 divided by 1/6. Keep, change, flip. Look at those watercolors. 1 times 6, 2 times 1, 6 halves, 3.